Hello, and welcome to this video about the number line. In this video, we will explore how to read number lines, draw and plot points on a number line, and add and subtract with a number line. Let's get started. We will use a number line to represent numbers in counting order. The number to the left is always smaller than the number to its right. To draw a number line, we first start by drawing a straight line, and then we put arrows at the ends. The arrows represent the fact that the number line goes on forever in both directions. When dividing the number line with tick marks, it is important to place the tick marks equally spaced apart. This shows that the distance from any two numbers is the same. For example, the distance from 1 to 2 is the same as the distance from 2 to 3. The most important number on a number line is 0, because every other number is based off of how far away it is from 0. Numbers to the left of 0 are negative, and numbers to the right of 0 are positive. Number lines continue infinitely in either direction, so the number line you see is always only part of the whole number line. Because of this, even though 0 is the most important number, it might not show up on your number line. For example, your number line might look like this if you're trying to plot the grade you got on your test. Number lines can be used to represent a specific number. In the example we just mentioned, we can use the number line to represent a test grade of 94 by putting a dot above the number like this. Plotting a negative number would happen the same way. Simply put a dot over the number you are wanting to represent. The number line here shows the number -5. We can also use a number line to help us add and subtract numbers. Movement to the right is for addition, and movement to the left is for subtraction. To use the number line for adding and subtracting, we start by plotting a point at our first number. Then we move right or left, depending on the operation, the number of spaces matching the second number. Let's practice by adding -7 plus 5. We will start at -7, and since the operation is addition, we will move to the right 5 spaces. As you can see, we land on -2. Therefore, -7 plus 5 equals -2. Now let's try subtracting 9 minus 4. We will start at the number 9 on the number line, and since the operation is subtraction, this time we're going to move to the left. We move left 4 spaces, which lands us on 5. Therefore, 9 minus 4 equals 5.
Why do we classify numbers? Why do we give them names like integers, irrational numbers, or negative numbers? For the same reason we classify anything. We want to make sure that everyone has an understanding of what specific numbers are called and what they mean. After all, there's a difference between 25 and -32 and 4 to the 6th power. In this Mometrics video, we'll provide an overview of numbers and their classifications. Numbers are our way of keeping order. We count the amount of money we have. We measure distance. We use percentages to indicate a sale. Numbers are an integral part of our everyday existence, whether they are whole numbers, rational numbers, or the first type of numbers we're going to look at, real numbers. A real number is any value of a continuous quantity that can represent distance on a number line. Essentially, it's any number you can think of. 50 is a real number. 1 billion is a very large real number. Real numbers encompass 3 classifications of numbers, which we'll talk about in a little bit. Whole numbers, rational numbers, and irrational numbers are all real numbers. Imaginary numbers are not real numbers. They are complex numbers that are written as a real number multiplied by an imaginary unit, I. For instance, the square root of -1 calculates as the imaginary number I, and the square root of -25 is 5i. Even though imaginary numbers aren't real numbers, they do have value. Electricians use imaginary numbers when working with currents and voltage. Imaginary numbers are also used in complex calculus computations. So just because these numbers are called imaginary doesn't mean they aren't useful. Whole numbers are numbers that we count with. 1, 2, 3, 4, and 5 are all whole numbers. So are -17 and 0. Whole numbers do not have fractions or decimals. All whole numbers are called integers. Integers can be positive or negative whole numbers. All integers and whole numbers are part of a bigger group called rational numbers. This group also includes fractions and decimals. That means that 3/5 and 7.25 are rational numbers. Rational numbers can also be positive or negative. Rational numbers have opposites, which are called irrational numbers. These numbers can't be written as a simple fraction. Pi is the most famous irrational number. We have a close approximation of how to calculate pi, but it's just a close approximation. Pi is renowned for going on and on forever. That's why it's an irrational number. You can't easily write it as a fraction. Natural numbers are those that are positive integers, although there is some debate as to whether natural numbers start at 0 or 1. Negative numbers are, well, exactly that. They are the numbers below 0. There are several other number classifications as well. Numbers are divided into even and odd numbers. If you can divide a number by 2, that number is even. So 24, 36, and 74 are all even numbers because if you divide them by 2, you get 12, 18, and 37. Even numbers always end with 0, 2, 4, 6, or 8. Odd numbers can't be divided by 2 and leave a whole number. Any odd number divided by 2 will leave a fraction. So 17 divided by 2 is 8.5. 23 divided by 2 is 11.5. All odd numbers will end in 1, 3, 5, 7, or 9. Numerators and denominators form fractions, which are comprised of 2 integers. The number on top is the numerator. The number on the bottom is the denominator. The numerator, the top number, shows how many parts we have. The denominator, the bottom number, shows how many parts make a whole. Let's say you have 6 apples and 3 of the apples get eaten. The number of apples you have left over would be displayed as 3/6. You would then divide 3, the top number, into 6, the bottom number, to determine the percentage of remaining apples. In this case, the number is 50%. So that's our look at numbers in their classifications. From whole numbers to irrational numbers, we need to know what to call numbers so we can know what they mean. Hey guys, welcome to this Symmetrics video on fractions. Fractions can be simple or complex. In this video, we'll cover different types of fractions and how to add fractions with different denominators. So, what is a fraction? A fraction is a part of a whole, which means a fraction can never be a whole number. Think of it like this. Our circle is divided into 8 equal pieces. Let's say 3 pieces were filled in. That means that 3/8 of our circle is filled in. The top number is called the numerator. And our bottom number is called the denominator. When saying fractions out loud, the denominator will usually be spoken as the ordinal version of the number. You would say 1/8 instead of 8, or 1/3 instead of 3. Let's take a look at a list of our denominators and see how we would say them. As you can see, there are a couple of exceptions. If our denominator is 2, you could say half instead of second. Or if our denominator is 4, you can say quarter instead of fourth. But either one is acceptable. Hopefully that helps you to understand how fractions are defined and also how to actually say them out loud. But there are different types of fractions. Let's take a look at those. First, we have a proper fraction. A proper fraction always has a numerator, which we looked at, that is smaller than the denominator. Our example that we used before, 3/8. So our numerator, 3, is smaller than our denominator, 8. Some other examples of proper fractions include 4/5, improper fraction is the opposite of a proper fraction in that the numerator is larger than the denominator. So while 3 over 8 is a proper fraction, 8 over 3 is an improper fraction because the numerator is larger than our denominator. Improper fractions are always equal to or greater than 1. That means that 9 over 9 is an improper fraction since it's equal to 1. There are also mixed fractions, which contain a whole number and a proper fraction. Here's an example. Note that the whole number 2 is followed by the proper fraction 3 over 4. We also have equivalent fractions. Equivalent fractions are two different fractions that name the same number. For example, 6/8 and 3/4 look different, but they're the same. 3/4 is just a simplified or reduced version of 6/8. To simplify 6/8, you just divide the numerator and the denominator by 2 to get 3/4. Now that we know the different types of fractions, we can explore how to add them. If two fractions have the same denominator, adding is a breeze. You just add the numerators together, and that gives you the answer. For example, so notice what we did to get 3/4. All we had to do was add from our first fraction the 1 from our numerator, and from our second fraction the 2 from our numerator. Add them together to get 3, and we just bring over our 4 from the denominator. Simple. But what happens if the denominators are different? Well, in that case, you have to convert the denominators to be the same. So let's take a look at an example. You can't really simplify 3/8 into anything that would easily add with 1/2, but we can do something with 1/2 that we could easily add with 3/8. And that's multiplying 2 by 4, which would give us 8. But whatever we do to our denominator, we also have to do to our numerator. So that would look like this. So our equation now becomes 3/8 plus 4/8 equals 7/8. Subtraction works the same way. If you're subtracting fractions with the same denominator, you can just subtract the top numbers, like in this example. So in this example, all we had to do was subtract our top numerators here, which gave us 2/4, which simplifies to 1/2. Simplifying numbers just makes them easier to work with. But if you're subtracting with a different denominator, you have to make the denominators match. For example, so in this example, 3/8 minus 1/4 is equal to x. We're kind of looking at a same issue like we did over here. We need our denominators to match. So we need to find out what can we do to make our denominators match. Well, in this case, we can multiply 4 times 2. But remember, we have to do the same thing that we do to the denominator, we must do to our numerator. So we can multiply it times 2, and then here's what we get. So once we multiply our second fraction here by 2, we get 3/8 minus 2/8, which gives us 1/8. So these problems were pretty easy because they had either the same denominator or were just really easy to convert. But let's look at one more equation that's a little trickier. So at first glance, it doesn't look like these numbers have much in common, such that we would be able to multiply or divide 4 by anything to get 7, or 7 by anything to get 4. So a lot of the times when you have problems like this, what you end up having to do is multiplying this fraction by the denominator of the other fraction. And likewise, we would multiply this fraction by the denominator of this fraction. So here's what that looks like. So after our multiplication, we end up getting a common denominator, which is 28. So now all we have to do is add our numerators together, which that gives us 45 over 28. And that's our answer. With this calculation, we found the least common denominator. The least common denominator is the smallest common number between denominators. Anytime you perform a calculation with different denominators, you must find the least common denominator to solve the problem.
Hi, and welcome to this review of fractions and mixed numbers. Before we dive in, let's review the basic parts of a fraction. Remember, a fraction simply represents a part of a whole. It has a numerator and a denominator, which tells us what the part is and what the whole is. Let's look at the fraction 3/4 as an example. We can see that the 3 is our numerator and the 4 is our denominator. So the fraction 3/4 is really saying 3 parts out of 4 parts total. It can also be helpful to visualize 3/4 as simply 1/4 plus 1/4 plus 1/4. It is very important to remember that a denominator of 4 does not represent the value of 4. A denominator of 4 represents the value of 1 that is divided up into 4 equal parts, or fourths. The type of fraction we're working with here represents a value less than 1 whole. 3/4 is not quite 1. If we had 4/4, that would be equivalent to 1. But we only have 3 out of 4 parts. We see and use fractions that are less than 1 all the time in our daily lives, whether it's for things like recipes or keeping track of time. Recipes often call for amounts such as 1/2 teaspoon of salt, and we often keep track of time in terms of quarter hours, like 3:15 for 3:15. Though we observe this type of fraction very frequently in our daily lives, it is not the only type of fraction. Consider the following scenario. You're ordering pizza for a big celebration. There will be lots of hungry guests at this celebration, so you order 3 pizzas. Each pizza is cut into 6 slices. This means that each pizza has 6 equal parts, and as a fraction, 6 would be considered our whole, or our denominator. If your first guest eats 2 slices, we would represent this as the fraction 2/6. 2 parts out of 6 parts total. But what if that first guest was really hungry and grabbed 7 slices? Again, each pizza was cut into 6 equal slices, so 6 remains as our whole, or denominator. But this time our part is 7. In this scenario, our numerator is larger than our denominator, 7/6. Fractions with a numerator larger than their denominator are referred to as improper fractions. Essentially, improper fractions equal a value that is more than 1. 1 whole pizza would be represented by 6/6, or 6/6. 7/6 represents 7/6, which is more than 1 pizza. This could be visualized as 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 equals 7/6. It can also be written in another form called a mixed number. An improper fraction and a mixed number will represent the same amount, but simply be written in a different form. For example, the improper fraction 7/6 could also be written as the mixed number 1 1/6. Mixed numbers and improper fractions share the same amount, but as a mixed number, the parts are collected and consolidated into as many groups of 1 whole as possible. For example, 4/4 would be grouped together as 1. 7/7 would also be grouped together as 1. Any value where the numerator is equivalent to the denominator would be expressed simply as 1. In our pizza example, the guest took 7 slices from a group of pizzas that were sliced into 6ths. We said this could be represented as the improper fraction 7/6, or visualized as 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. As a mixed number, we would group 6 of these 6ths in order to form 6/6, or 1 whole. By grouping 6/6 together, we can see that 1/6 is left over. We would write our mixed number as 1 1/6. Let's try a few more examples. Let's write the following improper fractions as mixed numbers. 4/3 can be visualized as 1/3 plus 1/3 plus 1/3 plus 1/3. We know that 3/3 is equal to 1, so let's group 3 of these thirds together. We are now left with 1 and 1/3 as our mixed number. 3 halves can be visualized as 1/2 plus 1/2 plus 1/2. We then know that 2 halves, 2 over 2, makes 1 whole, and we're left with 1/2 left over. So 3 halves as a mixed number is 1 and 1/2. Let's try one more example, 7/4. 7/4 is the same as 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4. Now we know that 4/4 are grouped as 1 whole. So these 4/4 pulled over to equal 1, and we're left with 1, 2, 3/4. 7/4 written as a mixed number is 1 and 3/4. This process will take place in reverse in order to convert between a mixed number to an improper fraction. For example, if we started with a mixed number 1 and 3/4 and we wanted to convert it to an equivalent improper fraction, we would take a look at the whole number. In this case, it is 1. This whole number is really representing the denominator that's in the fraction. In this case, it's 4, so the 1 is equal to 4 over 4. When we combine these 4/4 with the 3/4, we end up with 7/4 total, or 7 over 4. That's all there is to it. Hello, and welcome to this video about proportions. In this video, we will explore what proportions are and what it means for quantities to be proportional, and mathematical and authentic applications of proportions. Before we get into proportions, we need to quickly review ratios. Recall that a ratio shows the relative sizes of 2 or more quantities. For example, in the alphabet, the ratio of vowels to consonants is 5 over 21. In a standard deck of cards, the ratio of face cards to total cards is 12 over 52. In all circles, the ratio of the circumference to the diameter is pi. There are many ways to represent ratios. Here, we'll mainly be working with the fractional representation. Ratios are not exactly fractions, but they can behave just like them. Now on to proportions. A proportion states that 2 ratios are equal. If I want to cook 1 cup of white rice, I would combine it with 2 cups of water. In other words, for every cup of rice, I need 2 cups of water. So the ratio of rice to water is 1 over 2. If I wanted to double the recipe, I would need 2 cups of rice and 4 cups of water. So 1 over 2 is equal to 2 over 4. These recipes are proportional because this is a true statement. In other words, their fractional forms are equivalent. On the other hand, the recipe for brown rice calls for every 1 cup of rice, 3 cups of water. The recipes for white rice and brown rice are not proportional because 1 over 2 does not equal 1 over 3. Let's look at using proportions to find quantities. In a standard deck of cards, the ratio of face cards to total cards is 12 over 52. Dealers in casinos often use 8 decks for blackjack. How many face cards would they use? In 8 decks, the ratio of face cards to total cards is still 12 over 52. So these quantities of cards are proportional. There would be 96 face cards. Let's look at another example. The length of a rectangle is 4 units, and its width is 3 units. The length of a second rectangle is 8 units, and its width is 3 units. Are the rectangles proportional? Let's write this out. 3 over 4 does not equal 3 over 8. Since the ratios of length to the width are not equivalent, the rectangles are not proportional. Now suppose you're driving a car at 75 miles per hour, heading to a destination that's 300 miles away. That is, for every hour that passes, you drive 75 miles. In this case, distance is directly proportional to hours, because as hours increase, distance also increases, and the rate of increase does not change. This table shows an increase of 75 miles for every 1 hour. The graph shows a straight line intersecting the origin. The equation is of the form y equals kx, where k is the constant of proportionality. Here, the constant of proportionality is 75. Every hour amount is multiplied by 75 to calculate distance. Now let's consider the same journey but with a different relationship. You travel the same 300 miles, but instead of traveling at 75 miles per hour, you travel at 60 miles per hour. How much longer does the trip take at the slower speed? From the previous example, we know that y equals 75 miles per hour times by 4 hours equals 300. Now you are driving slower. So you have y equals 60 times x, which represents the number of hours traveled, equals 300. So to solve for x, you divide by 60 on both sides and get x equals 5. Here, distance is inversely proportional to time because as time increases, distance to the destination decreases. You get closer every hour. The distance doesn't change, so the constant of proportionality is 300. What does change is the speed. The graph shows all possible speed-time combinations to drive the 300-mile distance. If you drive 300 miles per hour, it would take you 1 hour. Whereas if you drive 1 mile an hour, it would take you 300 hours. Equations showing inverse proportionality have the form y equals k over x, where k is, again, the constant of proportionality. Here, the distance 300 could be divided by the number of hours to calculate the speed, or it could be divided by the speed to calculate the number of hours. Suppose you drove to the same place again, and it took you 3.5 hours. How fast did you drive? Well, you've got y, which is your speed, is equal to k, your constant of proportionality, which is 300, divided by the total number of hours, 3.5, and that gives you that your speed is roughly 86 miles per hour. Now that we've covered proportions, let's talk about percentages. When we deal with percents, they can be treated like proportions. The word percent literally means per 100. So knowing that, we can figure out any relationship we need to. The key to percents is figuring out the whole and the part. Simply put, the whole is the quantity represented by 100%, and the part is the piece of the whole represented by some other percent. Generally, proportions with percents look like this. The whole amount over 100 is equal to the partial amount over the partial percent. Your restaurant bill comes to $33.75. You received exceptional service, so you want to leave a 20% tip. How much do you tip? Using a bar model can come in handy when visualizing these problems. For instance, $33.75 over 100 is equal to whatever your tip is going to be over 20. So if you look, we can do 33.75 over 100 divided by 5 over 5, and that gives you 6.75 over 20. Since the total amount is proportional to the tip amount, we can simply divide the total amount by 5 to arrive at the tip amount. Division by 5 also makes sense because 20 is 1/5 of 100. Suppose you went back to the restaurant and had a bill of $26.34, but decided to leave the typical 15% tip. How much do you leave? The bar model still helps us visualize. So we have 26.34 over 100 is equal to our tip amount over 15. This time, it's not as easy as dividing by 5, since 15 doesn't go evenly into 100. Here's a different way of using equations to think about it. If 26.34 is equal to 100%, then 0.2634 is equal to 1%. From there, we're going to multiply both sides by 15, and you get 3.941 is equal to 15%. Now we know you left about $3.95. You visit a store that's having a 25% off sale. You pick out some clothes and your total comes to $140.67. How much would full price have been, and how much did you save? With a 25% discount, that means you paid 75% of the full price. So you have your original price over 100, which is equal to 140.67 over 75. If 140.67 is equal to 75%, so if you divide both sides by 3, you get 46.89 is equal to 25%. And then if you multiply both sides by 4, you get 187.56 equals 100%. The original price was $187.56, so you saved $46.89. Suppose your friend went shopping with you and used a coupon for an extra 10% off. This coupon was calculated after the total was calculated, so it came off the sale price. What was the total discount percentage from the original price if your friend spent $211.89? So if you have $211.89 is equal to 90%, then if you divide both sides by 9, you get 23.54 is equal to 10%. From here, you would multiply both sides by 10 and get 235.4 equals 100%. So 100% of the sale price equals 75% of the original price. So we have $235.40 is equal to 75% of the original price. From here, if you divide each side by 3, you'll get $78.47 is equal to 25%. Then we'll multiply both sides by 4 to get $313.87 is equal to 100%. We can figure out a percentage by simply dividing the part by the whole and then multiplying by 100. In this case, the percentage paid is the amount paid over the original price times 100. So from the previous example, we have this. This is the percentage your friend paid. 100 minus 67.5 is equal to 32.5%, which is the total discount percentage your friend saved. Hi, and welcome to this video about the algebra of polynomial and rational expressions. In this video, we will explore multiplying polynomials, factoring polynomials, dividing polynomials, rational expressions, and operations with rational expressions. Before we get heavily into polynomial algebra, let's recap a few important terms. A polynomial is a mathematical expression of one or more algebraic terms, each of which consists of a constant multiplied by one or more variables raised to a non-negative integral power, such as a plus bx plus cx squared. The key pieces to remember are, number 1, polynomials consist of one or more terms, of the general form ax raised to the nth power, that are added or subtracted. The sample in the definition has 3 terms. Number 2, the coefficients of the terms can be any type of number. And number 3, the powers of the terms can only be non-negative integers, including 0. Let's look at some quick examples. 2x squared minus 4x plus 5 is a polynomial expression, but 2x raised to the 2.5 power minus 4x plus 5 is not a polynomial expression. Why? Because of the decimal exponent. Remember, the exponents in a polynomial expression have to be integers. 0.4x plus 1 is a polynomial expression, but x raised to the negative third power plus 1 is not because of the negative exponent. Now that we've looked at some polynomial expressions, let's look at the different types. A monomial is a polynomial consisting of one term. For example, x and 2 are monomials. A binomial is a polynomial consisting of 2 terms. X plus 1 and x cubed plus 4 are both binomials. A trinomial is a polynomial consisting of 3 terms. 12x raised to the 4th power plus 3x cubed plus 1 is a trinomial. A degree is the highest exponent in a polynomial. 2 is a degree 0 polynomial. X plus 2 is a degree 1 polynomial. And x squared plus 3 is a degree 2 polynomial. Now let's move on to multiplying. One of the traditional methods taught for multiplying polynomials is FOIL. This method highlights the need for organization. Multiplying polynomials is an application of the distributive property. The key idea is that every term of each polynomial needs to be multiplied by every term of every other polynomial. One way to help visualize and organize polynomial multiplication is with an area model, which looks like this. Let's multiply 3x plus 4 by negative 2x minus 5. So 3x times negative 2x gives you negative 6x squared. And then 4 times negative 2x gives you negative 8x. Then here you get 3x times negative 5 equals negative 15x. And then here you have 4 times negative 5, which gives you negative 20. So the product is negative 6x squared minus 8x minus 15x minus 20, which then simplifies to negative 6x squared minus 23x minus 20. The area model demonstrates how to multiply every term of one polynomial by every term of the other, and it is expandable for polynomials of any size. Let's try another example. Our terms on the left are 7b to the 5th and negative 2b squared. And our terms on the top are 2a cubed, negative 4a squared, a, and negative 12. We need to simply multiply all the terms, then add the resulting terms together. None of these terms are like terms, so they can't be combined. So our answer is so this is our final answer. As we'll see throughout this video, working with polynomials is almost identical to working with simple numbers. When we think of factors, for example, we may think of numbers that are multiplied to create another number. For example, 2 and 3 are factors of 6. 20 and 5 are factors of 100. Often, we look for numbers' prime factorization. The prime factorization of 30 is 2 times 3 times 5. Because all the factors are prime numbers. Think of factoring as undoing the area model we just explored. Often, the terms of polynomials have common factors. Consider this polynomial. Each term has a common factor of 5a squared. So this can be rewritten as 5a squared times 4b plus 2a plus 3b cubed plus 1. This is the prime factorization of the polynomial. It cannot be factored any further. Sometimes factoring happens in groups. It appears as if this polynomial cannot be factored. Rearranging to group the a terms and the b terms, we have this. Pulling out the common factors, we have this. Now we can see the common factor of 2x plus 1. So we have this. 2x plus 1 times a plus b squared. We can always check our factoring work by multiplying the factors to be sure we end up with the original polynomial. Polynomial division is closely related to multiplication and factoring. Consider the number 6. Its prime factors are 2 and 3. 2 times 3 equals 6. So 6 divided by 2 is 3, and 6 divided by 3 is 2. This polynomial has prime factors of 3x plus 4 and negative 2x minus 5. Negative 6x squared minus 23x minus 20 divided by 3x plus 4 gives you negative 2x minus 5. And then if you do negative 6x squared minus 23x minus 20 divided by negative 2x minus 5, that gives you 3x plus 4. One polynomial can be divided by another as long as the degree of the dividend is greater than or equal to the degree of the divisor. Here's how it works. First, make sure the exponents of both polynomials are in descending order and put a 0 in for any missing in the sequence. For example, 2x squared plus 1 would be 2x squared plus 0x plus 1. Divide the first terms. Here, the question is, how many times does 3x go into negative 6x squared? Then, we're going to multiply 3x plus 4 by negative 2x. Then, we'll subtract the product. Then, we bring down the next term in the divisor, and we repeat. How many times does 3x go into negative 15x? Multiply, and then subtract. There's a remainder of 0, so negative 2x minus 5 and 3x plus 4 are factors of negative 6x squared minus 23x minus 20, as we already knew. Rational expressions are closely related to rational numbers. The word rational comes from the word ratio. Just as rational numbers are defined as having the form integer over integer, rational expressions are defined by the form polynomial over polynomial. Here are some examples of rational expressions. When common factors occur in the numerator and denominator of a rational function, they can be divided to make 1. This is often taught as canceling out, but it actually stems from the fact that, for example, 2 divided by 2 equals 1. We can remove the common factors from these rational expressions. Rational expressions behave like fractions. To add or subtract them, we need to get a common denominator. For example, since one expression has 3x as a denominator and the other has x squared, a common denominator of 3x times x squared can be created. Remember to multiply each numerator by the same factor so that we are essentially multiplying each expression by 1. Now multiply through and simplify. To multiply them, we multiply straight across. And to divide them, we multiply by the reciprocal. And there you have it. Hi, and welcome to this overview of quadratic equations. Before we dive into how to solve them, let's first talk about quadratic functions. When we graph quadratic functions, we'll notice that they can be used to tell all kinds of visual stories, from a daredevil shooting out of a cannon to a satellite dish listening to interstellar signals. Equations for these functions generally look like this: f of x, or sometimes y, equals ax squared plus bx plus c. And their graphs form a characteristic shape called a parabola, which looks something like this one. The different characteristics of quadratic functions that are most commonly analyzed are the vertex, which is the maximum or minimum value, the x-intercepts, which are also known as the zeros, and the axis of symmetry. Now that we have a little background, let's dive further into solving quadratic equations and interpreting the results. So what do we mean by solving? In this case, one of the things it means is to figure out which values of the variable, if any, make the equation 0. So instead of the function f of x equals ax squared plus bx plus c, we write the related equation. 0 equals ax squared plus bx plus c. In other words, the solutions to a quadratic equation are the values that make the quadratic function true when f of x, or y, is equal to 0. This is the function f of x equals negative x squared plus 2x plus 8. Every point on the graph satisfies this equation. Solving 0 equals negative x squared plus 2x plus 8 gives us two solutions, because the function equals 0 only when it crosses the x-axis. Here's another way to look at it. To solve a quadratic equation means to find the x-intercepts of the related function, also known as the zeros. Before you get started with any solving method, make sure your equation is written in standard form. Ax squared plus bx plus c equals 0. This will prevent errors and can provide insight into choosing the most appropriate method for solving an equation. If your equation is not in standard form, simply add or subtract terms as needed. For instance, 2x plus 8 equals x squared is not written in standard form, but by subtracting x squared from both sides, we get negative x squared plus 2x plus 8 equals 0, which is now in standard form. The first method we'll look at is graphing. If you have access to a graph or can easily create one using the internet or a graphing calculator, this can be a great method to use. Let's look at an example. Here is the graph of f of x equals negative x squared plus 2x plus 8. The solutions to the equation negative x squared plus 2x plus 8 equals 0 are x equals negative 2 and x equals 4. Solutions can always be verified by plugging them back into the original equation. Sometimes, quadratic equations can be simplified and solved by factoring. Looking at our sample equation, we have negative x squared plus 2x plus 8 equals 0. The left side can be factored into negative x plus 4 times x plus 2 equals 0. Now let's pause. There's a property called the zero product property that says that if there are two numbers whose product is 0, one of the numbers must be 0. In more mathematical terms, if a and b are real numbers and a times b equals 0, then a equals 0 or b equals 0. Makes sense, right? Back to our equation. Negative x plus 4 times x plus 2 equals 0 means that negative x plus 4 equals 0 or x plus 2 equals 0. So we solve both. We're going to subtract 4 from both sides, which gives us negative x equals negative 4, and then divide by negative 1. We get x equals 4. For this equation, we subtract 2 from both sides, and we're left with x equals negative 2. So our zeros are x equals 4 and x equals negative 2. These match what we found on our graph. Factoring is nice, but not every equation can be factored easily. Luckily, there are a couple more methods we can use, including the completing the square method. The idea behind this method is to create a quadratic equation that contains a perfect square, and then take the square root to find the solutions. Here's our equation again. Negative x squared plus 2x plus 8 equals 0. To complete the square, the equation needs to not only be in standard form, but the coefficient on the squared term needs to be positive instead of negative. So we divide all terms by negative 1 to get ready. This gives us x squared minus 2x minus 8 equals 0. First, move the constant term to the other side by itself. For this, we'll add 8 to both sides. This gives us x squared minus 2x equals 8. Pause. Now we need to add a number that creates a perfect square on the left-hand side. Let's consider some perfect squares. To complete the square in our equation, we'll need to add a number to both sides of our equation. In the examples, notice that the number is b over 2 squared. 4 equals 4 over 2 squared, 9 equals negative 6 over 2 squared, and 16 equals 8 over 2 squared. In our equation, we'll add negative 2 over 2 squared, which equals 1, since our b is equal to negative 2. Remember, an equation only stays equal if you change both sides in the same way. So since we're going to add 1 to our left side, we also need to be sure to add 1 to the right side. Now the left side can be factored. X minus 1 squared is equal to 9. Since we have a perfect square, we take the square root of both sides. On the right-hand side, we need to account for both positive and negative square roots. Now we'll split into separate mini-equations. X minus 1 equals 3, and x minus 1 equals negative 3. We're going to solve for x over here by adding 1 to both sides, which gives us x equals 4. And here we're going to do the same, add 1 to both sides, which gives us x equals negative 2. We get the same solutions as before. Completing the square can be used with any quadratic equation, but if you start with a perfect square and don't realize it, the equation will look the same after you use this method as it did when you started. There is one last method for us to examine. The quadratic formula, as you'll see, involves the most algebra, but it has two distinct characteristics. One, it can truly be used with any quadratic equation, and two, part of it can be used to determine how many solutions to expect beforehand. Here it is in all its glory. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. The piece of the quadratic formula under the radical, the square root sign, is called the discriminant. Calculating its value helps us know how many solutions to expect. Let's take a minute to consider how many times a quadratic function can possibly intersect the x-axis. This example shows twice. Sometimes it's only the vertex, and sometimes not at all. Because of the shape, these are our only choices. In order for a graph like this to intersect the x-axis more than 2 times, it would need to change direction again and thus no longer be a parabola. Now let's consider square roots in general. If the square root of a number is greater than 0, there are 2 real solutions. Taking the square root of a positive number yields positive and negative roots. If the square root is 0, there is one real solution, 0. Taking the square root of 0 is 0. If the square root of a number is less than 0, there are 0 real solutions. We can't take the square root of a negative number and end up with a real number. So what does this have to do with the discriminant? If b squared minus 4ac is greater than 0, then there are 2 real solutions, 2 x-intercepts. If b squared minus 4ac equals 0, there is one real solution. The vertex of the parabola is the x-intercept. And if b squared minus 4ac is less than 0, there are no real solutions, no x-intercepts. Using our ongoing example, negative x squared plus 2x plus 8 equals 0, a equals negative 1, b equals 2, and c equals 8. The discriminant d is b squared minus 4ac, which is 2 squared, minus 4 times negative 1 times 8, which is equal to 4 plus 32, which is equal to 36. Since 36 is greater than 0, we know that there are 2 real solutions to our equation, as expected. What's the point of calculating the discriminant? If you get in the habit of checking it every time, a few things happen. If there are no solutions to your equation, you'll know right away and can stop. If there are 1 or 2 solutions, the discriminant will serve as a check, regardless of the method used. If you use the quadratic formula, a chunk of it is already calculated. Speaking of the quadratic formula, let's try it out. Again, a is equal to negative 1, b is equal to 2, and c is equal to 8. Plus, we already know the discriminant. So we have negative b, which is negative 2, plus or minus the square root of the discriminant, which we found was 36, so the square root of 36, all over 2 times our a, which is negative 1. This is equal to negative 2 plus or minus 6 over negative 2. Now we're going to split it into 2 equations. We have negative 2 plus or 6 over negative 2, and negative 2 minus 6 over negative 2. This one is equal to 4 over negative 2, which is negative 2. This one gives us negative 8 over negative 2, which is equal to 4. So x equals negative 2 and x equals 4. We've seen all 4 quadratic equation solving methods in action. Now let's put some context around our practice equation. Suppose our function f of x equals negative x squared plus 2x plus 8 represents the height of a rock from the ground in meters you throw off of a small cliff as a function of time in seconds. We want to know how long it takes for the rock to hit the ground. In order to do that, we would solve the equation negative x squared plus 2x plus 8 equals 0, which we have already done many times over. Remember, the 0 represents 0 height. In function terms, this means on the x-axis. In this situation, that means on the ground. We know that our mathematical solutions are x equals negative 2 and x equals 4. In this situation, the solution of negative 2 doesn't make sense. What does it mean? 2 seconds ago? Travel back in time 2 seconds? We would state that the rock landed after 4 seconds. Hello, and welcome to this video about calculations using points on the coordinate plane. So first off, let's remember that a one-dimensional number line is a representation of all real numbers that extends infinitely in both the positive and negative directions and looks something like this. When two number lines intersect at a right angle at their zero coordinates, the two-dimensional coordinate plane is formed, which typically looks something like this. Generally, the horizontal axis is called the x-axis, and the vertical axis is called the y-axis. The point where the axes intersect is called the origin. Let's plot a point on the coordinate plane. The location of point A is given as a horizontal component x and a vertical component y, and written as x, y. From the origin, to get to point A, we would count 2 units to the right and 3 units up. So the coordinates of point A are 2, 3. Likewise, the coordinates of the origin are 0, 0. Since the coordinate plane is comprised of number lines, they can be viewed zoomed in or zoomed out as much as necessary to convey data or a story. For example, the x-axis here has been zoomed in. Because of the scale of the x-axis, the coordinate points of point B are 1/2, 3. And the x-axis has been zoomed in here, while the y-axis has been zoomed out. Because of the scales of the axes, the coordinates of point C are 0.2, 300. Using the coordinates of points on a coordinate plane, we can calculate the distance between 2 points. The distance formula, an application of the Pythagorean theorem, looks like this. In words, it's the square root of the horizontal distance squared plus the vertical distance squared. In this case, the formula can be used, but since points A and D lie on the same horizontal grid line, all we need to do is count squares. This also works for 2 points on the same vertical grid line. The distance from point A to point D is 6 because the 2 points are 6 squares apart. Using the formula yields the same result. In this case, we can see that the coordinates of point B are 1/2, 3, and the coordinates of point E are 3/2, -6. In order to determine the distance between the 2 points, we'll need to use the formula because the points do not share a grid line, so we can't simply count squares to determine the distance. In this case, we're going to need to estimate the coordinates of point F because it doesn't lie at the intersection of 2 grid lines. It is often the case that we need to estimate the coordinates of a point. Let's estimate point F to be located at -0.4, -350. Now let's use the distance formula to get a good idea of the distance between points C and F. Using the coordinates of points on a coordinate plane, we can also calculate the coordinates of a point that lies exactly halfway between 2 points, which is known as the midpoint. The formula for finding the midpoint coordinates looks like this. In words, it's easy to remember as the average of the x's, the average of the y's. As we saw previously, the distance between points A and D is 6. Half of that distance is 3. Since points A and D lie on the same grid line, the midpoint will lie there as well, at the coordinates -1, 3. We can verify this with the formula. Even though we can always calculate half of the distance between 2 points, that won't tell us the coordinates of the midpoint in this example like the formula does. To graph, we'll need to estimate the location of -3/2. Previously, we estimated the coordinates of point F to be -0.4, -350. Let's use the formula to estimate the midpoint between points C and F. To graph, we'll need to estimate the location of -25. Hi, and welcome to this video on linear equations. Today we will be looking at what linear equations are and how to solve systems of linear equations. Before we dive in, let's quickly review what a linear equation is. Remember that a linear equation describes a straight line on a graph. They generally look something like this: y equals mx plus b. The slope of the line is represented by m, and the y-intercept is represented by b. X and y simply represent an ordered pair that would fall on the graphed line for that equation. Here's an example of a linear equation and the graph to match. Remember that slope represents rise over run. So a slope of +3 represents a rise of 3 and a run of 1, up 3 and over 1. This example was already set up in what is called slope-intercept form. However, not all of the linear equations you work with will be conveniently set up this way. Sometimes you will need to manipulate the equation in order to get it into slope-intercept form. This process needs to occur before you can begin graphing. It's important to remember that when you are solving for variables within a linear equation, the objective is to use inverse operations in order to isolate each variable. For example, if you were solving for y in the equation 4 equals -2x plus y, the process would look like this. 4 equals -2x plus y. In order to isolate the variable y, we need to get rid of the term -2x. To do this, we use inverse operations. The inverse of -2x is +2x. So we add 2x to both sides, and we get 2x plus 4 equals y. If we reverse our equation, we get y equals 2x plus 4. Now the linear equation is in slope-intercept form, y equals mx plus b. It is now graphable because we have isolated the variable y. Now that we've reviewed linear equations, we can dive into the process of solving what we call systems of linear equations. By system, we just mean more than one equation. When we want to solve for a system of equations, we are essentially looking for the point of intersection when the equations are graphed. We have solved the system when we can locate the point where the lines meet. For example, the solved system for the linear equations x minus 2y equals -2 and 3x minus 2y equals 2 would look like this. Both equations are graphed and the lines intersect at the point 2, 2. That means that the ordered pair 2, 2 is our solution for the system of equations. The three common strategies that are used to solve systems of linear equations are graphing, substitution, and elimination. Let's focus first on the graphing method. This method has 3 main steps. Step 1 is to manipulate both equations so that they are in slope-intercept form, y equals mx plus b. Step 2 is to graph both equations, and step 3 is to identify the ordered pair where the lines intersect. Let's take a closer look at these 3 steps with an example. We are going to use the system y equals -3x minus 7 and y equals x plus 9. Remember, to solve this system, we need to figure out where the lines intersect when they're graphed. Let's try the 3 steps together. Step 1 is to manipulate the equations so that they are both in slope-intercept form. For this example, both equations are already set up in this form, so we are ready for step 2. Step 2 is to graph both equations. Let's look at the first equation, y equals -3x minus 7. The value -3 represents the slope of the line, and the value -7 represents the y-intercept. With these 2 pieces of information, we are able to build a line. Now let's graph the second equation on the same coordinate grid. Now we have both equations graphed, so we're ready for step 3. Let's locate the ordered pair where the lines meet. The graphing method is a convenient strategy visually because we can see exactly where the lines cross. We can see clearly that the lines intersect at the point -4, 5. So the solution for this system of linear equations is -4, 5. Let's try a tougher example where the equations are not already given to us in slope-intercept form. For this example, we'll use the system 3x minus y equals 4 and 7x plus 2y equals 18. First, we need to manipulate both equations so that they are in slope-intercept form, y equals mx plus b. Let's start with the first one. We need to isolate the variable y. So first we're going to subtract 3x from both sides. This gives us negative y is equal to negative 3x plus 4. Right now we have negative y. The negative in front of the y is essentially a negative 1 multiplied by y. We need to get rid of that negative 1 by doing the inverse. This means that we need to divide both sides of the equation by negative 1. This gives us y equals, and when we divide by a negative number for the whole equation, we can divide each of the numerator parts by negative 1. So negative 3x divided by negative 1 gives us 3x, and 4 divided by negative 1 gives us negative 4. So y equals 3x minus 4. Now y is on its own, and the first equation is in slope-intercept form, so it's graphable. Now let's isolate the variable y in the second equation so that we can graph both lines together. First, we're going to subtract 7x from both sides. That gives us 2y equals negative 7x plus 18. And we're going to divide by 2 on both sides. This leaves us with y equals negative 7 halves x plus 9. We can also write it this way. Y equals negative 3.5x plus 9. At this point, we have two equations that are both in slope-intercept form. Equation 1 is y equals 3x minus 4, and equation 2 is y equals negative 3.5x plus 9. Now we just need to graph both lines and determine where our lines intersect. Here's what our graph will look like. The system of linear equations is solved when you can identify the ordered pair where the lines intersect. We can see that the lines meet at 2, 2. If you are working to solve a system and the graphed lines end up being parallel, never intersecting, then the system has no solutions. Similarly, if you graph a system and the lines completely overlap each other, then the system has infinite solutions. The graphing method is often a really convenient way to solve systems. However, sometimes it can be more efficient to solve systems using the substitution or elimination method. These two methods use more of an algebraic approach. Let's first take a look at the process for using the substitution method. For this example, we'll use the system 3x plus 5y equals 13, and 2x plus y equals 4. The second equation appears to be easier to solve for y. So let's solve for y by using inverse operations and subtracting 2x from both sides. So this gives us y equals negative 2x plus 4. This is step 1. Step 2 is when we take this value of y, which is negative 2x plus 4, and we plug it into the y of our other equation, equation 1. This is the substitution process. So we have 3x plus 5 times negative 2x plus 4 equals 13. Now step 3, solving for x. You will use the distributive property and inverse operations to solve for x. First, distribute the 5, multiplying it by negative 2x and 4. From here we have 3x minus 10x plus 20 equals 13. Now combine your like terms. 3x minus 10x gives us negative 7x plus 20 equals 13. Now we're going to subtract 20 from both sides. This gives us negative 7x is equal to negative 7. Now we divide both sides by negative 7 and get x equals 1. We're halfway there. Now we just need to use this value of x to solve for y. Here's step 4. We know that x equals 1, so let's plug this in for x in the equation y equals negative 2x plus 4. So we have y equals negative 2 times 1 plus 4. Now we're going to simplify. So y equals negative 2 plus 4, which equals 2. Now we see that y equals 2. So the solution for this system of equations is 1, 2. Another way to solve systems of equations is using what's called the elimination method. For this method, you first need to manipulate the equations so that the variables are on one side and the constants are on the other. Let's use the systems x equals y plus 5 and 3x plus 2y equals 5 for this equation. Using inverse operations, the first equation becomes x minus y equals 5. And the second equation looks ready to go as is. Now all of the variables are on one side and the constants are on the other. The objective of the elimination method is that when you add or subtract the two equations, one of the variable terms will be completely canceled out, leaving us with a much easier equation to solve. For example, 5x would cancel out with negative 5x. Let's look closely at both equations. Remember, we are going to be choosing whether to add or subtract both equations with the goal of eliminating one of the variable terms. Eliminating a variable term simply means having a coefficient of 0. Notice that if we multiply all parts of our first equation by 2, the term negative y would become negative 2y. This is helpful because the negative 2y will cancel out with the variable term 2y in the other equation, and eliminating variables terms is our goal. Let's try it. We'll multiply all parts of the first equation by 2. This turns this equation into 2x minus 2y equals 10. We manipulated the equation in this way because now we are set up for the term negative 2y and 2y to cancel each other out when the two equations are added together. The variable will be eliminated, and this will leave us with a simpler equation to solve. We chose to add the two equations and not subtract them because the goal is elimination. If we add the equations, the terms cancel out. If we subtracted the equations, we would still be left with negative 4y. So let's write this equation over here. 2x minus 2y equals 10. And we're going to add the equations together. When the 2y and the negative 2y cancel out, we are left with 3x plus 2x is 5x equals 5 plus 10 is 15. Now what we want to do is divide both sides by 5. And we get x is equal to 3. Now that we know that x is 3, we are halfway done. In order to find y, we simply plug in our value of x into one of our equations and solve for y. So let's plug 3 into the equation x minus y equals 5. We plug in 3 for x minus y equals 5. Subtract 3 from both sides, gives us negative y equals 2, and divide by negative 1. Y equals negative 2. This means that the solution to our system is 3, negative 2. In this example, we chose to add the two equations in order for the variable terms 2y and negative 2y to cancel out. However, there are times when you would need to subtract the two equations instead. You would choose to subtract the two equations in a situation where you had two variable terms that were the same, such as 3y and 3y. Okay, before we go, let's quickly review what we learned. Linear equations describe a straight line on a graph and are usually seen in slope-intercept form, y equals mx plus b. We can solve systems of linear equations by using one of three methods. When using the graphing method, you first manipulate both equations so that they are in slope-intercept form. Then graph both equations and identify the ordered pair where the lines intersect. The substitution method works by taking one of the equations, solving for one of the variables, and then plugging the solved variable into the other equation. When using the elimination method, you either add or subtract the equations to eliminate any one variable from the equations. A parabola is the distinct shape of a quadratic equation when it is graphed. In this video, we'll give you some clues found in quadratic equations that can tell you more about the parabolas they graph. So the symmetry of a parabola is due to the squared term in the quadratic equation. However, there is one point on the parabola that does not have a mirror image. This point is called the vertex and is notated by the ordered pair hk. The vertex is either the maximum or the minimum value of the parabola, depending on which direction the parabola opens. When the x variable is squared in a quadratic equation, the parabola will open either up or down. Picture the two symmetric branches of the graph extending away from the vertex in the same direction, either up towards positive infinity on the y-axis or down towards negative infinity on the y-axis. However, when the y variable is squared in a quadratic equation, the parabola will open either to the right as both branches extend away from the vertex towards the positive infinity on the x-axis, or to the left towards negative infinity on the x-axis. To understand this further, we need to look at how quadratic equations are written. They are written using two basic forms. A standard form quadratic equation is written as y equals ax squared plus bx plus c, where a represents the coefficient of the squared variable, b is the coefficient of the linear term, and c represents a constant. Because the x variable is squared, this is a quadratic function which opens either up or down. A quadratic equation in this form with the y variable squared would be written as x equals a y squared plus by plus c. The parabola graphed from this relation would open either left or right. A quadratic that is in vertex form is written as y equals a times x minus h squared plus k, where a is the coefficient of a squared binomial, which in this example contains the x variable, and the vertex of the parabola is the ordered pair hk. If graphed, this parabola would open either up or down. The equation for a left or right opening parabola in vertex form would be written as x equals a times y minus k squared plus h. As you can see, the a value is a common element in both forms of the quadratic equation. This value holds the key to which direction the parabola will open. If the a value is positive, equations with the x variable squared will graph as parabolas that open up. Equations with the y variable squared will graph as parabolas that open right. If the a value is negative, equations with the x variable squared will graph as parabolas that open down. Equations with the y variable squared will graph as parabolas that open left. To put all of this information together, let's look at a few examples of quadratic equations. First, we're going to look at y equals 2x squared plus 3x minus 6. This is a standard form quadratic equation with the x variable squared and a equals 2. Because a is greater than 0, the parabola will open up. The next one we're going to look at is y equals negative 4 times x minus 3 squared plus 2. This is a vertex form quadratic equation with the x variable squared, vertex at the ordered pair 3, 2, and a equals negative 4. Because a is less than 0, the parabola will open down. Our third equation is x equals 3y squared minus 2y minus 1. This is a standard form quadratic equation with the y variable squared and a equals 3. Because a is greater than 0, the parabola will open right. And our last equation is x equals negative y minus 2 squared plus 1. This is a vertex form quadratic equation with the y variable squared, vertex at the ordered pair 1, 2, and a equals negative 1. Because a is less than 0, the parabola will open left. Thanks for watching and happy studying.